So we've mentioned that water is amphoteric. It can act as an acid or a base. It can actually do this with itself. So this is called the autoionization of water. So here we have a water molecule and a water molecule. This water molecule can act as an acid, and this one can act as a base. So this one donates a hydrogen ion to this one. And so what we end up with is hydronium ion and hydroxide ion. Does that seem a little odd? Why would it do that, right? We've seen so many situations where in order for something to happen, you have to have two different things, right? You don't have one water molecule just deciding to give a hydrogen ion to another water molecule. You would expect these two to get together and form two water molecules. And that is actually what happens most of the time. So this is an equilibrium, and the equilibrium constant for this is very small, which tells us that this only happens a little tiny bit. But the important thing is that it can happen. Yeah.
Is that why the pH of water is usually neutral?
This is why the pH of pure water is neutral. Yeah. Okay, there it went. Just make sure I didn't miss one. Okay. Having issues. Well, that was dumb. Now I can't go forward again? No, I am forward. Never mind. Okay, so here we're writing that reaction just using hydrogen ion instead of hydronium ion. So we understand that this water molecule is donating the hydrogen to another water molecule. It's just that we're not showing that here. And then we've got hydroxide ion. Is everybody okay with that? Because I know it's a little confusing. It's just, mom and dad, they're going out, and exactly who the babysitter is, does that play into it very much? I mean, you get somebody who's good, and you don't really care who it is. Maybe you don't have kids. But we're talking about what's happening here, and you need someone, but exactly which one of your great babysitters it is doesn't matter. So this is given to a water molecule. We don't care which one. So we can write an equilibrium constant expression for that reaction. And that would be the concentrations of the products divided by the concentrations of the reactants. But wait, the concentration of the reactant is a pure liquid, and so it doesn't show up in the equilibrium constant expression. So we've got H plus times OH minus, and that's our equilibrium constant. Or we can write the H plus as H3O plus. So this is called Kw. It's the ion product constant for water. Because it's the product of the ions, and it's a constant, and it's for water. Yes, ion product constant for water, Kw. I don't care if you're really on top of the exact name for that, but Kw is hydronium ion concentration times hydroxide ion concentration. So, of course, equilibrium constants depend on temperature. So we specify the temperature most of the time. At 25 degrees, Kw is 1.0 times 10 to the minus 14. So that's small, right? There's not a lot of this happening, this autoionization. So in pure water, every time you get a hydrogen ion, you will also get a hydroxide ion, and so their concentrations have to be equal. Does that make sense? So in pure water, those concentrations are equal, and they are equal to the square root of Kw. So they are each 1 times 10 to the minus 7. So if I call this, how to explain this? So if I say the H plus concentration is equal to the hydroxide ion concentration, and I'm going to call that X, then this expression here is the same as X squared. And the equilibrium constant, this ion product constant for water, is 1.0 times 10 to the minus 14. And so if I want to know what X is, We got the square root of that. It's not any big crazy thing. So the concentrations of ions in pure water are very small. 10 to the minus 7. But that's not 0, right? For most purposes, it's essentially 0. It doesn't really matter, but it isn't actually 0. So pure water is neutral because we have equal concentrations of hydronium and hydroxide ion. In an acidic solution, we have an acid. And so the acid creates additional hydronium ions, and that causes the ion product constant that still applies, and so the equilibrium is going to shift when we add acid. I feel like there should be something written here. Let's look at this. So if we write out this autoionization of water, if I add an acid to this solution, the acid is going to produce hydrogen ions. So I'm adding hydrogen ions here. What does that do to this equilibrium? It causes it to shift to the left. The added hydrogen ions are going to react with some of the hydroxide ions to reform water. If I add a base to the solution, if I add more hydroxide ions, it's also going to cause the equilibrium to shift to the left. And some of those hydroxide ions are going to react with these hydrogen ions. So what we have in an acidic solution is the hydronium ion concentration, the hydrogen ion concentration being larger than the hydroxide ion concentration. And the opposite is happening in a basic solution. You've got more hydroxide ions than hydrogen ions. That make sense? So using that ion product constant expression for water, we can calculate the concentrations of the ions if we know what one of them is. So here we're saying this is at 25 degrees Celsius, and they're giving us hydroxide ion concentrations, asking us to find the hydronium ion concentration and identify, is this solution acidic, basic, or neutral? So we're using this Kw equals hydronium ion concentration times hydroxide ion concentration. I'm given this hydroxide ion concentration, and I'm trying to find this one, so I'm going to rearrange this equation and say that the hydronium ion concentration is equal to Kw divided by the hydroxide ion concentration. So I took this expression and I divided both sides by hydroxide. So then, to find the hydronium ion concentration, I take Kw, 1.0 times 10 to the minus 14. That is one that you should remember. 1 times 10 to the minus 14. And I'm going to divide by this 1.5 times 10 to the minus 2. And again, equilibrium constants don't have units, but the concentrations are always in molarity. So we've got 1e minus 4 divided by 1.5, e minus 2. I'll stick with 2 sig figs, 6.7 times 10 to the minus 13. That make sense? Yeah.
What happened to the formulas with log? I thought you used log for this kind of stuff?
We will do logs with this, but not yet.
Okay.
Yeah, that's coming. So then we're also asked, is it acidic, basic, or neutral? Well, in an acidic solution, the hydronium ion concentration is larger than the hydroxide. In a base, the hydroxide is larger. Now, with these negative exponents, it's easy to get these backward. So this is 10 to the minus 2, and this one's 10 to the minus 13. Which one's smaller? This one, the 10 to minus 13, is smaller. So this is a basic solution. So this one's basic. Here, letter B. The hydroxide ion concentration is 1.0 times 10 to the minus 7. We actually don't have to do the calculation for this one, because in pure water, the hydronium ion concentration and the hydroxide ion concentration are both 1.0 times 10 to the minus 7. You can do the, yeah, it's neutral. You can do the calculation, you'll come up with this, and we say that that's a neutral solution. It's not acidic or basic. And then this one down here, let's predict acidic, basic, or neutral just looking at the hydroxide ion concentration. So what we're looking at, is this larger or smaller than 10 to the minus 7? It's smaller. This is a lower concentration than in a neutral solution, and so this must be acidic. So this is acidic, and let's calculate. So the hydronium ion concentration is Kw divided by the hydroxide ion concentration. One 1.2 times 10 to the minus 5. This concentration, 10 to the minus 5, is larger than 10 to the minus 10. So more acid, this is an acidic solution. Because of the autoionization of water, if the hydroxide ion concentration goes up, the hydronium ion concentration goes down. If the hydronium ion concentration goes up, the hydroxide ion concentration goes down. So they're sort of inversely related. Well, actually, they are exactly inversely related. So you wanted to know about logs, here they are. So the pH scale. The pH, and this is just something we defined. Oh, she left? I waited till she left to talk about it because she asked about it. She'll come back and be mad. So we made up this function, pH, and the pH is the negative base 10 log of the hydronium ion concentration. And just because we defined it that way. In general, this lowercase p stands for negative log of, and so we can do it for hydronium ion concentration, we can do it for hydroxide ion concentration, we can also do it for things like calcium ion concentration. Then it would be a pCa instead of a pH. So in a solution with a hydronium ion concentration of 5.3 times 10 to the minus 8, we can calculate the pH. pH is equal to negative log, and that's not an inverse log, it's a negative sign times the log. Here's your logarithms. The negative log of that concentration. So my calculator, I'm going to press the negative sign, the base 10 log button, 5.3 EE minus 8 equals, and I get 7.2757. And then significant figures. Well, our concentration had two significant figures. In a logarithm, it's only the numbers to the right of the decimal point that are significant figures. The numbers to the left of the decimal point are related to the exponent on the times 10. And so those are equivalent to place holding zeros, and so the 7 is not considered a significant figure. So I should call this 7.28 as my pH. I am not going to get on you about that, but I'm going to use it, and if you're wondering why, that's the reason. So let's just do a little example here. What if I had 5.3 times 10 to the minus 2? Well, then the pH would be 1.28. Do it on your calculator.
Is it always going to be the 0.28?
If the, what part is that? If this 5.3, if it's 5.3, it'll always be 0.28.
Okay, so it's like 5.5, it'll be just under 5.
Yeah, so this 7 is 1 less than the 8.
Yes.
This 1 is 1 less than the negative 2. So that's how I was able to do it without actually pulling out the calculator. So if we had 5.8 times 10 to the minus 13, then the pH would be 12.28. So this 0.28 comes from the significant figures. That's supposed to be a 3. These are the sig figs. These are the sig figs, and so those show up after the decimal point. And the 12 is from this 13. So that's why the significant figures are the way they are. We use a pH scale because the range of concentrations of hydronium ion are so huge. I mean, it's like 14 orders of magnitude. And so if you're trying to graph stuff, it's just difficult. So we can go from 10 to the minus 14 in concentration to 10 to the 0, which would be 1 molar. It's a huge range. So when we take the negative log of this, we break this down into a scale that's 0 to 14. So in the middle, when you have a neutral solution, you're going to have a concentration of 10 to the minus 7. The negative log of 10 to the minus 7 is 7. Logarithm is what is the power that I raise 10 to get this number. Can you go more in this direction? Can you go to higher hydrogen ion concentrations? Yes, you can. You can have higher than 1 molar. In fact, in the stockroom, we've got 18 molar sulfuric acid. Well, it's way more than 1 molar. So what would the pH of that be? It would be negative. So it's possible to have negative pHs. That just means it's very acidic. So calculate the pH of each solution to indicate whether it's acidic or basic. So here we've got the hydronium ion concentration. So the pH is the negative log of that. It's going to be 8 point something. So log 9.5, EE minus 9, 8.02. This number has 2 sig figs, and so I want to have 2 decimal places because that's where the sig figs are. Is this acidic or basic? It's basic. So it's good to be able to think about this in several different ways. We can look at the hydronium ion concentration and say, well, that's less than 10 to the minus 7, which would be pure water. So if I have less hydronium ion, then I have more hydroxide ion. We should also be able to look at the pH. If the pH is above 7, it's basic. If it's below, it's acidic. Here we've got the hydroxide ion concentration, and it wants the pH. Well, the pH is not the negative log of the hydroxide ion concentration. So we have to calculate the hydronium ion concentration. Like we did previously. I'm getting 1.408 times 10 to the minus 12. And then we can calculate the pH. $11.85. Any questions? We'll learn how to do this in Chem 3A. Okay, what if we have a pH and we want the hydronium ion concentration? Well, the equation that we know is that the pH is equal to the negative log of the hydronium ion concentration. We want hydronium ion concentration. Okay, so we've had a crash course in logarithms, right? How do we get rid of a logarithm?
Base 10.
Base 10, the anti-log, right? 10 to the x. So what I want to do is I want to move the negative sign to the other side. I'm going to multiply both sides by -1. So negative pH equals the log of the hydronium ion concentration. Are you okay with that? And then, to get rid of the log, I do 10 to the x of both sides. So 10 to the x on the left side is 10 to the negative pH. And then I have 10 to the log of the hydronium ion concentration. And the log and the 10 to the x cancel out, so that's just hydronium ion concentration. So there's another equation. H3O plus concentration equals 10 raised to the power of the negative pH. So for this example, the pH is 8.37, so I've got 10 to the negative 8.37. So I'm going to do my 10 to the x button and put in negative 8.37 and press equals. Now my calculator is showing me 1, 2, 3, 4, 5, 6, 7. It's showing me 8 zeros and a 4. Psst, 8, 4. Are there no digits past the 4? There are digits. My calculator's in decimal display mode, and so it's able to display it just barely, and so it does. But I know that there's got to be more digits than that. So what I'm going to do is I'm going to put it in scientific notation. And now it's going to show me 4.26579519 times 10 to the minus 9. So your calculator will kind of trick you sometimes. There's two things you can do. You can put it in, tell your calculator to show it to you in scientific notation, or you can make note of, okay, it's 10 to the minus 9, and then multiply that by 1,000,000 or something, just to move the decimal point over so you can see the rest of the digits. So when I express this concentration, how many significant figures should it have? So I'm coming from 8.37, I'm taking the anti-log of that, and I'm gonna get this number. How many of these digits do I show? Only two. In this logarithm, this pH, the digits after the decimal point are the significant figures. So I'm gonna call this 4.3 times 10 to the minus 9 molar. Yeah. Okay, that's a good question. How do you do scientific notation? So on the TI-36X Pro, press the mode button, and it'll bring up a whole bunch of stuff, and never go over to radians or grads. If you go to the second line, it says norm, psi, and eng. So go over on the psi, and then just hit enter, and then do quit, and then you're like, oh dang, I have to do the whole calculation over again. No, just press enter again, and it'll bring your number in. To go back, you do mode, move the cursor down to normal, press enter, quit, enter, and it'll put it back. Other calculators do it differently. It's good to be able to go back and forth. Any other questions? So we've got the pH scale. We also have the POH scale.